Vitamin B7 is also known as biotin, and to look at the structure of biotin, you're going to see that it has a little fatty acid tail on the bottom in a way, and that has a carboxylic acid group at the end, and then it has this weird ring structure which contains a urido ring on the top and a sulfur ring on the bottom. That is the structure of biotin, and biotin deficiency is very rare. Some symptoms are like cracked nails and stuff, and you're going to have the inflammation, like acne, some spotty skin, and red eyes and stuff like that. It's quite a rare deficiency. It's found in most foods. One place where it's not really found so much is egg whites. Egg whites contain a protein known as avidin, which binds to biotin and means that it cannot be absorbed inside of the gut. Now, avidin is destroyed by cooking and heat, and it's denatured, and so that means when you digest eggs when they're cooked, avidin is not able to bind to biotin and therefore can be absorbed. But for eggs in general, it is normally found in quite a high quantity inside of the egg yolk anyway. But that's just a quite interesting thing because it is really found in most foods: leafy vegetables, grains, meat, all that sort of stuff. It's a bit like pantothenic acid, which is found in most things. And it's a deficiency that when it comes to supplements and specific things about that, you don't really have to worry about it at all. Now, biotin's function biochemically is for carboxylation reactions, not decarboxylation reactions, but carboxylation reactions. This is where a CO2 group is added onto the molecule rather than taken away. And the nitrogens on the urido ring are the active part of this molecule. Now, the active molecule, I suppose, is something known as carboxybiotin. Now, carboxybiotin, the carboxy group is bound to one of the nitrogens on the urido rings, but carboxybiotin is formed in quite an interesting way. You're going to need a HCO3-, which is bicarbonate, and an ATP molecule to get this started. You're going to have the third phosphate group on the ATP, which is stabilized by a magnesium ion. The O- on this HCO3, O- will attack the phosphorus, which is very, very delta positive. Because it's more electronegative than phosphorus, these oxygens are sort of taking the electrons and bringing them closer to them. And because there is 4 oxygens bonded to it, and so it's going to be very, very delta positive. Oxygen, O- attacks this very delta positive phosphorus, and that causes the bond to break between ATP and the third phosphate group, so it becomes ADP, and the phosphate is then bound to this HCO3 in this weird kind of complex. Eventually, it will figure itself out and CO2 will be released. This CO2 will then bind to one of the nitrogens on biotin, kicking the hydrogen off. That is carboxybiotin, and then carboxybiotin can donate this carboxyl, I suppose, group in a weird sort of way to a molecule that requires it. There are some uses of carboxylation reactions inside of the biochemical processes in the body. If you think of pyruvate and oxaloacetate, pyruvate can turn into oxaloacetate using this reaction. Normally, pyruvate would turn into acetyl-CoA, and then it will be combined with oxaloacetate to form citrate in the citric acid cycle. But pyruvate can also turn into oxaloacetate straight up, which gives a good supply of oxaloacetate for the body as well as acetyl-CoA. But to get from pyruvate to oxaloacetate, you have to add this CO2 group onto it, and that is done by an enzyme known as pyruvate carboxylase. And I'm going to go through the mechanism of how the biotin adds the carboxyl group onto oxaloacetate now. Now, a threonine amino acid, which is inside of the active site of the enzyme, will come along and kick the carboxyl group off of the biotin and bind itself to the biotin molecule. Then an O- will attack the H of a pyruvate. It then forms an alkene, a CH2 group. This alkene, because it's so electron rich, it contains 4 electrons alone inside of the double bond. The carbon of the carbon dioxide is very electropositive. Because, as I mentioned before with the phosphorus, you've got 2 oxygen double bonds. That's 4 electrons in each, and then all these 4 electrons in both bonds are being drawn towards the oxygen at quite a sort of unsymmetrical place, because oxygen is very, very electronegative compared to carbon. That means this carbon is so delta positive that this alkene will attack the carbon very, very easily. That carbon is going to form a bond with the carbons in that alkene. One of its bonds with the oxygen is going to stay as a CO carbonyl double bond, and then one of the bonds is going to split and just become an O-, because that means that it's oxaloacetate. That is the sort of, because it would normally be oxaloacetic acid, but there is no H plus involved. That's already been disassociated because that's often how these reactions are sort of looked at and done in a biochemical sense. Now, another reaction where biotin and its carboxylation function can be used, obviously the same exact thing is going to happen again with the ATP and the HCO3, carboxybiotin, etc., etc. And then acetyl-CoA carboxylase in fatty acid synthesis. Acetyl-CoA can turn into malonyl-CoA using biotin as a cofactor because acetyl-CoA needs that CO2 group added onto it to become malonyl-CoA. The exact same thing is going to happen to the biotin with the threonine amino acid kicking the CO2 off, and then the acetyl-CoA is going to be deprotonated to become a carb anion, not a carbocation, a carb anion. So the carbon has an extra electron, which means that it is negative. This lone pair can sort of accept dative bonds, but it's also negative, and so it will attack things that are electropositive. As I spoke about before, the CO2 is very electropositive, so that carb anion is then going to attack the carbon inside of the carbon dioxide, and because it's a carb anion and has the lone pair extra carbon, one of the CO bonds are going to break, and oxygen will take both of those bonds inside of that single bond that broke as part of the double bond. It's not like the bond has fully broken, just one of the bonds has broken, but it's taken both electrons inside of that one bond, and if that makes any sense. So that's going to leave an O minus, and then the carbon is then going to be able to bond to the acetyl-CoA to become malonyl-CoA. That is very useful in fatty acid synthesis, and without biotin, you can't synthesize those fatty acids. You're not able to obtain oxaloacetate and sort of bypass acetyl-CoA in that pathway in a way. But there are about many other functions of biotin inside of the body. I just wasn't going to go through the mechanisms of all of them because this is basically how it works. It's just there's going to be a different negative thing. Something will have to be very electron rich or negative or something like that, delta negative, to be able to attack that carbon dioxide in the enzyme's active site. That's essentially going to be the difference between mechanisms in every single kind of carboxylation reaction that involves biotin. Whatever is attacking the C is going to be slightly different. But with that, I recommend subscribing for more content like this, and have a good day.